Imagine you're driving on a highway, cruising at full speed. Suddenly, you reach an intersection, and you're unsure whether to turn left or right. You hesitate, and the cars behind you are forced to slow down. That's exactly what happens in a processor when it encounters a branch instruction. In pipelining, this hesitation is called a control hazard. Whenever a program encounters a branch, whether conditional or unconditional, the processor must decide where to go next. But making the wrong decision can cause costly delays. So how does the CPU deal with this? In this video, we'll break down how control hazards occur, why branches cause pipeline stalls, and how different branch prediction techniques, from basic static methods to advanced dynamic predictors, help processors make smarter, faster decisions. First, we will examine instruction hazards caused by unconditional branch instructions. Whenever there is an unconditional branch in a program, one clock cycle becomes idle because the processor needs time to calculate the target address and update the program counter. This idle time is referred to as the branch penalty. To address this issue, many processors use an instruction queue, which stores multiple pre-fetched instructions in advance. It also uses a decode unit, which retrieves instructions from the queue and sends them to the execution unit for processing. The decode unit not only identifies whether an instruction is a branch instruction, but also calculates the target address for branch instructions and fetches the necessary operands for execution. Since there's no condition on the branch, the target is known beforehand. The instruction queue and decode unit recognize where the program needs to go and directly redirect the control flow to the target instruction. This effectively skips the actual branch instruction, making the process faster and more efficient by maintaining the flow without any unnecessary delays. This method of leveraging the instruction queue and decode unit to streamline the handling of unconditional branch instructions is called branch folding. The second type of branch instruction is the conditional branch instruction. A conditional branch relies on the outcome of a given condition. This introduces additional complexity. Unlike unconditional branches, it is impossible to predict if the branch will occur before executing the preceding instruction. Older processors use techniques like delayed branching and static branch prediction to handle instruction hazards. Delayed branching is a technique used in some processors, especially RISC architectures, to minimize branch penalties by executing instructions that come after a branch, regardless of whether the branch is taken or not. These processors were specifically designed to execute one or more instructions after a branch statement before actually jumping to the branch target. Instead of immediately jumping to the new address when a branch is encountered, the processor executes one or more instructions in the delay slot after the branch before the jump takes effect. This allows the processor to keep the pipeline busy, reducing stalls caused by control hazards. There are two important things to understand when dealing with delayed branching. Most processors that implement delayed branching use a single delay slot. However, some processors allow more than one instruction in the delay slot. In this example, we assume that the processor has a single delay slot. So, the instruction after the branch instruction will be executed regardless of the result of the branch condition. The second step involves identifying an instruction that can be safely executed after the branch instruction without affecting the program's logic. Then, we move this instruction to the delay slot. By moving the shift left instruction into the delay slot, the program's logic remains unchanged. As we've seen, the pipeline typically stalls when a branch instruction is encountered because the instruction immediately following it must be discarded. However, by utilizing this position as a delay slot, we can prevent the pipeline stall and improve efficiency. The effectiveness of delayed branching depends on how often it is possible to reorder the code. While techniques like delayed branching help reduce stalls, they are not always effective, especially for deeper pipelines. Static branch prediction offers a simple yet effective way to improve performance by making fixed assumptions about branch behavior. Instead of waiting to evaluate the condition, the processor predicts the branch outcome in advance based on predefined rules. Since static branch prediction does not require extra hardware like dynamic branch prediction, it is a lightweight and fast solution, though it may not always be accurate. Now, let's explore how different static branch prediction strategies work. we will examine 3 static branch prediction methods. The choice of which method a computer uses is not made on the fly. Instead, it is determined in advance by system designers or the compiler, based on what they believe will work best for typical programs. This decision depends on an understanding of program behavior, performance goals, and trade-offs. With branch always taken, the processor predicts that every branch, like an if that jumps somewhere, will take the jump. It starts grabbing the next instructions from the jump's target spot instead of the next line. If it guesses right, the pipeline stays smooth. If it's wrong, it has to toss out the wrong instructions, go back, and grab the right ones, which takes a little extra time. It works well because lots of branches, especially in loops, do get taken, so the guess is often a winner. In this code, the branch is taken 5 times and not taken once. Branch always taken is right 5 out of 6 times, a solid score. Loops like this are common, and they usually jump back until the condition changes, so this prediction keeps things moving fast most of the time. But if the code had lots of if statements where jumps rarely happen, it might guess wrong too often and slow down. With the second method, the processor bets that the branch condition will fail, so it keeps fetching instructions right after the branch instead of the jump target. If it's right, the pipeline flows smoothly. If it's wrong, it has to backtrack, toss out the wrong instructions, and fetch from the jump spot, costing a bit of time. This method shines when branches usually don't happen, like if statements for rare errors. Many programs contain error handling code that only executes in exceptional situations, such as when an input is invalid or a hardware failure occurs. Since these errors rarely happen under normal conditions, assuming the branch will not be taken is usually correct. The third type of static branch prediction is based on the direction of the branch and is commonly known as the BTFNT prediction. A branch is an instruction that changes the flow of execution, typically based on a condition. Branches can be classified into forward and backward based on the direction they move in the instruction sequence. The most common type of forward branches are conditional statements like if, else, and break. The most common type of backward branches are loops like for and while. In BTFNT prediction, all backward branches are predicted as taken, while forward branches are predicted as not taken. In this code, the program contains both loops, backward branches, and conditional checks, forward branches. The backward taken, forward not taken prediction is useful for this type of code, where loops and conditionals exist together. In modern processors, dynamic branch prediction has replaced static methods like BTFNT, but BTFNT remains a good heuristic when no information about a program's actual execution behavior is available. Static branch prediction is simple and effective in many cases. However, static prediction has a major limitation. It makes the same decision for every branch, regardless of past behavior. What if we could make smarter predictions based on actual execution history? This is where dynamic branch prediction comes in. Dynamic branch prediction is a technique that uses the execution history of the instruction to predict the outcome of a branch instruction. We will look at 2 types of dynamic branch prediction. The first type of dynamic branch prediction is the local history-based prediction. Let's consider a simple program with a loop. We use a 2-state machine to describe the algorithm. Initially, the predictor starts in the likely not taken LNT state. If the loop branch is taken, that is I less than 10, it transitions to likely taken LT state and stays there until I equals 10 when it moves back to LNT state. This causes a misprediction when the loop runs again, as it starts in the LNT state. To improve accuracy, we introduce 2 more states, strongly taken ST and strongly not taken SNT. If a branch is taken multiple times in a row, the predictor moves from likely taken LT to strongly taken ST, making it more confident that the branch will be taken on the next iteration. Similarly, if a branch is not taken repeatedly, the predictor transitions from likely not taken to strongly not taken. These states ensure that a single unexpected outcome doesn't immediately reverse the prediction, improving accuracy. All these states are stored in the branch lookup table. As the loop executes, The predictor now moves from LNT to LT to ST, ensuring it remains in LT after exiting the loop instead of resetting to LNT. This reduces mispredictions when the loop restarts. Now let us look at the second type of dynamic branch prediction, global history-based prediction. Branching instructions in programs often follow predictable patterns. However, some branching behaviors are more complex and require a different prediction approach. This is where techniques involving a global history register, GHR, a pattern history table, PHT, and a saturating counter come into play. Let's look at how these components work together to improve branch prediction. Consider a simple program that checks whether numbers in an array are even or odd. Since a given set of numbers can be even or odd, we need to detect patterns in the input to have a better prediction. So, a special register called the Global History Register, or the GHR, is used to keep track of the previous input. For example, if the GHR is a 2-bit register, it will be initialized with the value 00. If the first input is even, it will be updated to the value 01, indicating that the last input was even while the one before it was odd. In the next iteration, if the input is odd, the GHR will be updated to the value 10, which signifies that the last input was odd and the one prior to that was even. In this way, we can keep track of the history of the inputs and try to detect any useful pattern. Now that we have the GHR to record the history of the input, we need another table that would predict the outcome based on these inputs. This table is called the Pattern History Table, or the PHT. The PHT serves as a lookup table for the GHR. Therefore, the GHR and the PHT will have the same number of entries. For example, if the GHR is a 2-bit register, the PHT will have 4 entries as 2 bits can produce 4 values. The main component of the PHT is the saturating counter. Saturating counters are a type of counter used in branch prediction and other applications to represent a limited range of values while preventing them from exceeding that range. The counter increases or decreases in response to events, like branch outcomes, but once it reaches a specific limit, it saturates and does not change further in that direction. For example, in a 2-bit saturating counter, the possible values are 00, 01, 10, and 11. The counter can increment and decrement based on certain conditions. If the counter reaches the maximum value, 11 for a 2-bit counter, it cannot be incremented further and saturates at that value. If the counter reaches the minimum value, 00 for a 2-bit counter, it cannot be decremented further and saturates at that value. Each value of the saturating counter in the PHT has a meaning, as shown here. The prediction algorithm can change the value of the entries and will adjust these values to yield a better prediction. Now, let's walk through how this prediction mechanism works using the branch prediction concept. At the beginning of the program, the GHR starts at 00, meaning we haven't seen any branches yet. The PHT is initialized with 4 entries, one for each possible 2-bit GHR value. Each PHT entry is associated with a prediction, as shown here. The PHT is initialized to some prediction. Let's say all entries are 01, weakly not taken. The first number is 2. The value of the GHR is the initial value, 00, so we use this as the lookup value in the PHT. The PHT entry for 00 is 01, which means the algorithm predicts that the branch will not be taken or the number is odd. Since the number 2 is even, the branch is taken. Because the prediction was incorrect, the PHT entry for the state 00 is incremented to 10, weakly taken. This adjustment indicates that we are now less confident in the current prediction, prompting us to alter the algorithm to predict in the opposite direction next time. Before we move on to the next input, the GHR is updated to 01, as the last number we encountered was 2, which is even. The second number is 3, and the GHR value is 01. We use this value to look up the PHT, since every entry in the PHT is initialized to 01, which indicates weakly not taken. The prediction would be not taken, and this is correct. As a result, the PHT entry for 01 is decremented to 00, indicating that we have increased our confidence in the current prediction. Next, the GHR is updated to 10 because the last input is odd, while the one before it is even. The third iteration has the number 4 as the input. Since the GHR has the value 10, we use this value to look up the PHT, which predicts the outcome as weakly not taken. Since the prediction is false, we increment the entry to 10, weakly taken, altering the algorithm to predict in the opposite direction next time. The GHR is now updated to 01. The fourth iteration has the number 5, and using the value of 01, we look up the PHT. The prediction is that it is not taken, which is correct. However, we do not change the PHT entry for 10 as it already reached the saturation point. Finally, we updated the GHR to 10. The fifth iteration has the number 6 as the input. We use the value of 10 to look up the PHT. The prediction is that the branch is weakly taken, which is correct. So we increment the entry to 11, strongly taken, and update the GHR to 01. After several iterations, we can get a reasonably accurate prediction for this type of branching instruction. Modern processors use distinct tables or table sets to specialize in different branch patterns, all stored in fast on-chip SRAM. This modularity boosts prediction accuracy across diverse code. Modern CPUs use hybrid predictors that blend local and global history. A chooser table decides which predictor is more accurate for a given branch, adapting to different workloads. This dual approach, refined over decades, keeps pipelines flowing efficiently across diverse code patterns. Thank you for watching the video. I hope you learned something today. Have a beautiful day, and see you in the next video.